Welcome for our tutorial videos on building climatized spaces. In this tutorial, we will review the principles of low-cost but efficient climatization for BSF production, especially for the growing part, which is an extremely intense process. Let's start with the key factors of a successful BSF production and what is the role of climate condition. We will discuss about why traditional HVAC systems are not optimal and in many cases lead to production failures. We will go over separately the role of optimal temperature, humidity and CO2 levels, and the core principles of efficient climatization for growing larvae. Finally, we will review different module sizes and pros and cons of each. As the larvae growing phase is the most intense and challenging, we will focus on it. But the same principal rules apply for breeding and nursing as well. Black soldier fly production includes many phases, especially if the breeding and nursing is part of it as well. Your goal is to produce as systematically and as low cost as possible larvae and fast. Then you'll post-process larvae to different forms for the customers. Even though systematic production is key, you will succeed or fail based on the substrate you use for the larvae growing. If the substrate is low quality or costs too much, you cannot do much on the production efficiency to make it better. Another critical factor, if you breed yourself, is to have systematic, scalable, and cost-efficient production of 5-day-old larvae. These are your critical input costs for each load. Outside the technical aspects of production, these are the critical factors first to get right. In the production side, the next key factor is the climate control. Larvae and flies are sensitive insects, and their ability to perform is directly proportional to temperature, humidity, and stable CO2 levels. Remember that larvae lives in the food, so the conditions of the substrate are key, not conditions in the air. However, as it is easier to measure air conditions, we need to extrapolate substrate conditions from it. Finally, a key factor of a successful BSF production and business is to find a match between your customer's expectation and your value proposition so that the price allows you to make a profit and still make the larvae product competitive. The remarkable aspect of BSF larvae is that they eat and grow extremely fast. This means going from a mouse to an elephant in a week, and that mouse eating 3 tons of food and pooping 2 tons. As all this can happen in a very confined space with 80% filled with larvae and substrate, this creates a huge challenge for keeping optimal conditions. Even a slightly non-optimal temperature could extend the growing period by 30% and produce larvae half the size. Another important aspect to understand is that as the larvae live in the substrate, and the initial conditions of the substrate is very wet, the temperature difference to air is 4 to even 5 Celsius. So if you aim for 30 Celsius at the beginning of the growing cycle, the larvae are exposed to about 25 Celsius. This temperature is not optimal for larvae. At the end of the cycle, the situation is reversed. As the substrate has dried and larvae are large, the process is so intense that it generates heat from the trays, even close to 40 Celsius. So now it is important that the air temperature is as cool as possible. The substrate should be wet and remain wet as long as the larvae are eating. This means that the air humidity should be kept over 65, preferably over 70% relative humidity. But at the same time, not over 80% as water would start condensating too much. There are a lot of misconceptions around CO2 levels. Larvae can withstand and thrive even at 8,000 ppm. The key is to keep CO2 levels stable in a process that is constantly changing requirements and need. We at Mana Insect have tested many commercial HVAC systems before realizing that we needed to build our own control logic. Traditional HVAC systems are designed for stable conditions with either some humans or produce inside. They mainly focus on temperature, but there are models that handle also humidity and even ventilation. However, they are not designed to control fast, intense changes and don't understand the CO2, temperature, and humidity needs of larvae growing. You can make an HVAC system work, but based on our practical experience, it will be 3 to even 5 times more expensive and 2 to 4 times more power consuming for the production capacity you can achieve with alternative way. Additional challenges with integrated HVAC systems are that they are never on optimal capacity, take long time to order, require professionals for installation and maintenance, and cannot be easily upgraded if needed. BSF production requires a climatization solution that is flexible and allows easy maintenance and upgrade options. As already mentioned, we need to care about the temperature of the substrate, where larvae live, and not air temperature. However, measuring substrate temperature is much more difficult Thus, we can use the air temperature to estimate the substrate temperature. Larvae are cold-blooded, so their activity is directly proportional of the temperature. In principle, the higher the temperature, the better, until you start damaging cells. We recommend having 35 Celsius at the beginning of the growing cycle, so that the substrate temperature is 30 or 31 Celsius. This will boost the small larvae to start eating faster. So for latter 4 days, it is recommended to keep air below 30 Celsius. BSF larvae have no teeth, so they need the substrate to be as mushy and liquid as possible. However, as they live in the food, it cannot be so liquid that they are swimming in it. To find the optimal balance of the substrate moisture and not let it dry up too fast, the air humidity has an important role. Humidity should be kept between 65 to 75 relative humidity for the whole growth duration. Don't worry about trying to dry the substrate by air, as it doesn't work. The larvae will dry the substrate while eating, and the job of HVAC control is to keep air ready to absorb it. There's no reason to try to dehumidify air to below 60% relative humidity, unless this occurs naturally at the end. But never go below 65% for the first 5 or 6 days. Many people misunderstand the role of CO2 and ventilation when it comes to larvae growing. We humans tend to become unproductive above 1500 ppm and drowsy over 2000. So we think that larvae require low CO2 levels as well, as exchanging air between outside and the climatized module is the main cause of power consumption. Because that air needs to be most likely manipulated with equipment, we want to minimize it. This means keeping CO2 levels as high as possible. For larvae, even 8000 ppm levels doesn't seem to cause any issues. However, we prefer to suggest keeping levels below 6000 ppm. The key is to keep levels stable, as the larvae are very sensitive to changes. If CO2 changes drastically, even at low levels, the larvae will try to escape their current location. But if CO2 levels are high but stable, the larvae are fine. Here are core principles of low-cost and efficient climatization solution. You need insulation, even if you are in a warm country. Actually, especially if you are in a warm country, you want to separate the space as much as possible from outside conditions. Insulation is the way to achieve this. More separation, the less power you will need to keep conditions optimal. Select insulation material based on the maximum difference you can have between inside and outside. For example, if temperatures can go to 10 Celsius or 50 Celsius with sun effect, then you can have at worst 20 Celsius difference to optimal larvae growing conditions. It will be a more cost-efficient and easily upgradable module if you use separate equipment for each role, meaning heater for heating, AC for cooling, dehumidifier for drying, and so on. Avoid integrated systems, which include all in the same hardware. Especially ventilation should be separately controlled. You don't want to have incoming and exhaust on at the same time, and to be also responsible mixing the air inside. You want to control incoming, exhaust, and internal circulation fans separately. As larvae growing process requires maximum capacity in only a short period of the 7 to 10 day period, it is beneficial if you know the outdoor conditions for that period. If temperatures will rise to high levels, you need to start cooling sooner inside, as otherwise you cannot control inside temperature and larvae will panic. To avoid failures, start using the space first with 50% capacity. For each successful round, add more trays and check if all conditions can be kept within limits. When you reach a point that one or more of the factors cannot be kept in boundaries, you know the bottleneck and can add more capacity, like heating or cooling. Here are some guidelines on how to think the volume size per climatized module. You might be tempted to make it as big as possible, but you should understand a few issues with this mindset. Use cost per cubic meter as your metric for both investment and operational costs. Operational costs will not come down linearly when you increase the volume, as prices of equipment and their power consumption are non-linear. So there are only a handful of fixed volumes where equipment costs, power consumption, and size are optimal. Efficient at 3 to 8 cubic meter spaces. This means a small greenhouse or a room. This is because you can only fit a few trays and the larvae don't cause such a high requirements for air conditioning. Container size module, which is about 35 to 45 cubic meters. This is extremely cost-efficient size, as you can still use low-cost and consumer-level equipment that are widely available. After that, you need to go much bigger to get back to same cost per cubic meter than the shipping container level module. We hope this video gave you a basic understanding of the principles of low cost and effective climatization.